All right, so today's lesson is going to be on work and power for fluids. Okay, again, we've done work and power before, but we're going to apply it to fluids. So there's a couple new terms, a couple new equations. The first is volume flow rate. So volume flow rate is a term used to sort of help understand the movement of fluid in a system. And it's given the symbol, the variable Q subscript W equals, and this is like the rate at which volume flows by. So try to imagine a pipe, and you can have a fluid moving through that pipe, a certain volume per time. All right, so let me go over an example. Our first example is going to be like this. This might help explain it. The first example, we have a water jet cutter. It needs a flow rate of 3.3 liters per minute and a time of 18 seconds to cut a certain metal component. So we have sort of this nozzle that's going to shoot water out of it, and it needs to shoot water out at a rate of 3.3 liters every minute. So that's the volume flow rate. That's what QV is. It's 3.3 liters per minute. It needs that much water coming out every minute. Now, volume flow rate says what's the volume of the water required. So we know time. It's 18 seconds. And we want to find volume flow rate. So if we look at our equation, just volume, we can use a triangle for this one, where volume is our volume flow rate over time, times time. All right, so if we look at this equation, volume equals our volume flow rate times time. We have to multiply the two. But if we just multiply the two together, you're going to notice something's happening with the units. So let me write this out and let's pay attention to the units. Our volume flow rate is 3.3 liters per minute. I'm going to write it like this, multiplied by 18 seconds. So volume is in liters. But if we multiply this, we get liters times seconds divided by minutes. So what we need to do is we need to change minutes into seconds. So if we multiply, put 1 minute on the top, divide it by 60 seconds, that's just multiplying it by 1, right? Because that ratio is 1. It's just the units that are different. But 1 minute is equivalent to 60 seconds. But now that we've done that, minutes will cancel, seconds will cancel, and we'll get units of just liters. And in this case, you'll get 0.99 liters. So that's the volume required. About 1 liter if you round it. All right. So let's go back to the PowerPoint. So this is the example of the water jet cutter. You'll have a nozzle and it will shoot water out at a volume flow rate, so volume per time, of 3.3 liters per minute. Okay, and I actually have solved the question in the PowerPoint as well. So let's skip that because we've done it. That should be meters cubed, by the way. So 1,000 liters is equivalent to 1 cubic meters. Change that. Oh, no, can't. All right. Fluid speed is another thing. So how are we going to talk about fluid speed? Let's just go with what we know so far. So speed is distance over time. Then I replace distance with volume over area. Why did I do that? So let me try and explain that. Let me just go to a blank piece of paper here. I'm not too great at 3D drawings, but let's try to imagine we have a pipe. You couldn't even see that. There we go. We have a pipe. Now let's say you have one molecule of water goes from here to here, travels some certain distance, delta D. Well, if you can follow that one molecule of water, then great. You can do distance, figure out how much time it takes, right? And you can get velocity or speed. But it's kind of hard to follow one molecule of water. So instead you follow the entire fluid. Now this entire cylinder has a certain volume, okay? And it also has a certain, at any point, if we sort of just look at one, call it a cross-sectional area. Now that cross-sectional area A, that's a circle if this is a cylindrical pipe. It equals pi r squared. Now you could label the entire dimensions of this, which would be the volume, as this area multiplied by the whole length, which we called the displacement. So area times displacement. Now if I rearrange that and divide by both sides by area, you get volume over area equals our displacement, or the distance down the pipe. So this is why I replaced displacement with volume over area. Now if I just bring that area down to the denominator here, you'll notice we have volume over time. Well, that's our volume flow rate. So you can think of speed as simply volume flow rate divided by that cross-sectional area. So let's try an example with this one. So there's our equation. Speed is volume flow rate over area. And this is another equation we can use a nice triangle for. Oh, I messed this up in my note too. That should be cubed. So making our triangle, you get our volume flow rate equals speed times area. Now this one I tried to make this V extra big because sometimes students will get confused because there's two V's. And a capital V doesn't look too dissimilar from a lowercase v, but our capital V is volume and our lowercase v is speed. So just be careful with that. Okay, let me just pause there to see if anyone has any questions. So using this equation, we're going to go over the second example. Question 2. Question 2 says, if the radius of the water jet cutter from question 1 is 0.34 millimeters, what is the speed of the water? So we want to know speed. That's just from our equation. V equals our volume flow rate over area. Now our volume flow rate we know because it's from question 1. The area though, well, if this is just a nozzle, we can probably assume that that area is a circle. The cross-sectional area is a circle. So to figure out the area, we need to first do pi r squared, where this is going to be r, so it says the radius. So our speed then, we can write as QV, volume flow rate, over pi r squared. That's our speed. Okay. Now again, we don't want to throw millimeters into our equation. So if we convert this to meters, right? A millimeter is a thousandth of a meter. So we can move the decimal over to the left 3 spaces to give us 0.00034 meters. So calculating for speed then, we get QV, which was from the previous question, 3.3 liters per minute. And again, I'm just going to focus on the units. Divided by pi r squared. So pi times r Now R we've already converted, 0.0034, one more zero, meters. But this will give us an answer of meters per minute, because we have a minute there. So we're going to multiply by 1 minute for every 60 seconds. So our minutes will cancel. This will give us a speed of 150 meters per second. Okay, so that's our fluid speed. All right, now a couple of things I want to sort of recall from our memory is the terms pressure, work, and power. So pressure, if you remember, is force over area. Work is force times distance. And power is work over time. Now we can play with these equations a bit. Because work is force times displacement, I can take that and replace it for this work term in power. So now power equals force times distance over time. But distance over time is speed. So I can write power as force times speed. So let's try some questions with this. We're going to go back to that water jet cutter. It's a long question with many parts. So question 3. If the water jet cutter from questions 1 and 2 exerts a force of 120 newtons, find the following. First, the pressure. All right. Pressure equals force over area. And a force is 120 newtons. And area is pi r squared, or pi times, oh, I forgot to square this up there. It's all right, I put it in my calculator properly. Times 0.00034 meters squared. Okay. Since everything is in our base units, we will get an answer in pascals, which is 3.3 times 10 to the 8 pascals. Now the power, that's pressure. Power, I'm just going to write as a large P here. And again, to distinguish between pressure and power, we seem to have like a lot of capitals and lower cases in this lesson, is force times speed. The speed we know is 150 meters per second, and force is 120 newtons. So to figure out the power, we're going to simply multiply them. And if you remember, the units of power is watts. All right, so now let's try to put it all together and answer question number 4. Question number 4 says, liquid in a cylinder exerts a pressure of 10,000 kilopascals. So let's write down what we know here. So pressure is 10,000 kilopascals on a piston of radius 8 centimeters. So radius is 8 centimeters. The piston moves 34 centimeters in 6.8 seconds. Okay, so first we need to find the force. Let me just continue writing what we know. It moves a distance of 34 centimeters in a time of 6.8 seconds. All right, part A. Find the force on the piston. Okay, well, we know pressure, and we know radius, so with radius we can calculate area. If you remember from this equation, pressure is force over area. And we can rearrange that to find force, because multiplying both sides by area, you get force as pressure times area. Pressure is 10,000 kilopascals, but I'm going to multiply that by 1,000 which would be 1 times 10 to the 7 pascals, multiplied by area, which would be pi r squared, or pi times, I'm going to write this, divide by 100 to put it into meters, which would be 0.08 meters squared. And that'll give us our force of 2 times 10 to the power of 5 newtons. So that's part A. Now part B, I'm going to write it down here. Part B wants to know the power of the system. Okay, now power we can write as force times speed. Now, we've just calculated force. We don't know speed, but we do know distance and time. And speed is just distance divided by time. So we can write it as force times by distance over time. Which equals, so we have 2 times 10 to the 5 newtons multiplied by, again, we're going to change this to meters, so 0.34 meters over 6.8 seconds. When we do that, we get 1 times 10 to the 4 watts. Okay, so a lot of math in this question, a lot of new terms, but we're going to do some simulations tomorrow to help